So, shall we start, sir?
Yes, we can.
Yeah, yes, sir. As very good morning and hearty welcome all the participants and distinguished speaker Dr. Rupan Goswami to the second session of the 5-day webinar on Indian seismic codes. So, hearty welcome Professor Sivya Murthy sir, Jaya ma'am, Satish Kumar sir, and Raghukant sir, and other delegates. So let me give a brief introduction about Rupan Goswami. He's an associate professor of Department of Civil Engineering, IIT Madras. His BE honors Civil Engineering, Jadavpur University, MTech and PhD from IIT Kanpur, and specialized in earthquake-resistant design and nonlinear behavior of structures. He started his career as structural design engineer and joined IIT Madras during 2008. He is a member of Earthquake Engineering Research Institute, Oakland, California, and a life member of Indian Society of Earthquake Technology, Roorkee, and a life member of Indian Road Congress, New Delhi. He has authored books prepared towards capacity building of architects, engineers, and artisans, supported by Gujarat State Disaster Management Authority. So he has carried out many research and consultancy works in seismic connections and capacity building in earthquake behavior of RC buildings. His research interests are seismic design of buildings and bridges, seismic design codes. And today, Dr. Rupan Goswami will be discussing on rationale behind provision of Indian seismic codes. So over to you, sir.
Thank you so much, madam. And good morning to everyone. I can see Professor Jaya. Good to see you. Murthy is here. Professor Satish Kumar, Professor Raghukant, and everyone, all colleagues out there. As you mentioned, madam, yesterday, that probably I'm the only one who have not visited your campus, but unfortunately, because of Corona, this could have been an occasion, but I'm stuck here. So my apology for that. But I'm glad everyone is here with us, with me. And so I will speak upon, as you said, the rationale behind provisions of not just Indian, but most seismic design codes in general. But of course, the focus will be on our Indian codes. So I was thinking, what should I speak about? Because yesterday, Professor Murthy gave a very, basically gave the overview. So I thought I will pick 3 items and then focus on that. And this particularly probably will be useful for our student friends because for them, this is the starting point and this is the important thing aspect. So what are these 3 items? Essentially, the focus on displacement as a loading. I'll kind of try to reinforce that thought. Second, of course, is the important concept of capacity design, which Professor Murthy showed that our current design codes, use or focus on. And the third item that I want to talk about is something a little more practical, which are the so-called multi-story buildings that we are building in our country today. So these 3 are the items that I will be focusing on today. And of course, there are many more issues. And we have, Professor Raghukant, Professor Jaya, and Professor Satish Kumar, who will definitely offer much more than what I will be able to touch upon today. So to begin with, let us just look at this, that we have this force loading and we have displacement loading. And I will try to reinforce this thought through a simple example. Let us just assume that we have a simple beam, simply supported beam, and we apply a concentrated load at midspan, elastic material, prismatic section, everything. So if we do this, we all know that there will be deflection and we should be able to calculate this deflection. If it is an elastic analysis, this is second year or first year mechanics or second year analysis. So everybody should be able to calculate this deflection. So the important point here is that when a load is applied on a structure, displacements or deformations are caused. Now let us take the same example, beam, and let's say we tie a belt or something at midspan and pull it down to produce a displacement delta. What will happen now? I'm sure everyone will realize that there will be forces which will get generated in the system, right? So when forces are applied on a structure, displacements are caused. Similarly, when displacements are imposed, forces are induced. And this is a very important concept that students have to, get used to. That's the first part. What is the second part? And this is the tricky one. In the first case, if I say the load is applied at midspan, everybody will be able to tell what that deflection will be. If the length is L, if I say the flexural rigidity is EI, so, so in that case, sorry, everybody will be able to very quickly tell what the deflection is. Now, if I say in the right side case, if I say that delta is unit displacement, how quickly can somebody come up and say what will be the reactive forces R1 and R2? Of course, R1 will be equal to R2 if that is the displacement is applied at midspan. This will take some time, and this is where our teaching, our education has to focus on. We teach the first part, we don't teach the second part. To even conceive that when a displacement is applied, forces will be induced, and the second level is to compute how much that force will be, is something that we have to get used to truly understand earthquake resistant design. Now, let me take this one step forward. So let's say we have two simple, steel bars. And in the first case, as you can see, I'm applied a force. And as I apply an axial tensile force, there will be some axial displacement. And we all will be able to calculate that. And as I go on applying, increasing the force, I will see more and more displacements. Very good. In the second case, now I'm pulling it. And so again, just like in the first case, there will be some reactive forces, because if I say this is the axial bar and this is the support, as I'm pulling it, I have to have a support reaction getting developed. So that is the force that gets generated again in the bar, and that is the support reaction. What is the big difference here? The difference is in what happens post yield. So in the force, this is what is called force control system, where the loading is force. A force is applied. As the force is gradually increased, deformation increases, but we cannot apply a force beyond the capacity. And the important thing is the margin between where the system yields, if it yields, and the maximum force that can be applied is limited. But the same situation, same case, if a displacement is applied, it is possible to apply large displacements, much more than what the yield displacement is, provided we make the system ductile. And that is the important thing, that this margin can be increased to a large extent by making a system what we call ductile. So what is this ductility? In the first figure is the load deformation response of a so-called brittle system. So as load is increased or as deformation is increased, it reaches a maximum and then suddenly it fails. That means the load capacity drops. Whereas in the second case, even after the system yields, it continues to sustain that load over a large displacement or deformation. And it is this plastic deformation, post yield deformation, that is important. And that is the measure of the ductile behavior of the structure. So we define ductility capacity as the ratio of the ultimate ductility, deformation to yield deformation. Note here that this point where it effectively yields, beyond that signifies damage. So ductility comes only after damage has occurred in the structure. An elastic structure, there is no exhibition of ductility in an elastic structure. So when we talk about ductility, damage is inherently in that behavior. Why are we talking about all this? Because as we all know that earthquakes essentially cause shaking of the earth, which is nothing but shaking at the base of the structure. And The bigger the earthquake, the larger is this shaking. And this shaking is nothing but movement at the base of the structure. So essentially, it is a displacement loading acting on the structure. What will be the, how much will that displacement be or the shaking be? That depends on how big the earthquake is. And so there can be a very small level of shaking, there can be a medium level of shaking, or there can be large displacement imposed at the base of our structure. How do we measure that? One of the ways is, of course, we talk about magnitude as a measure of the size of earthquakes, and there are different, magnitude scales. I will not go into the details of it. So one of the most common one, we all know that we use is the Richter's magnitude, which depends, which is measured based on the how big is the peak in an accelerogram data. And based on that, the size of an earthquake is usually denoted. Uh, of course, every earthquake is unique and they have different amplitudes, they have different durations of shaking, and of course, the frequency content, which was also mentioned yesterday by Professor Murthy. So they are all unique. But the question lies, how does it matter if there is a very big, for instance, a Chile earthquake, which is a very large, amplitude and duration? Did we in India feel anything when the Chile, such a big earthquake happened in Chile? Of course not. So is magnitude really that we should be thinking about as structural designers, as engineers? Answer is no. And that is why we talk about something else, and that is the intensity of shaking. Essentially, we try to look at what is the zone of influence of an earthquake and how big the shaking has been in that particular zone of influence. Needless to say, so therefore, we use another measure, another scale for measurement of earthquake size, and that is intensity. And there are again many intensity scales. We generally use the MSK scale as a standard mostly. So for instance, what you see here is that this is the isoseismals of Bhuj earthquake. So there is a zone which experienced maximum intensity of shaking. That is the maximum shaking displacement that structures felt in that particular region. And as you move further away from each other, that place, the intensity of shaking decreases. So structures are designed for intensity of shaking and not for magnitude of earthquake. So when I hear a question, if you hear a question, for what magnitude of earthquake is this structure designed for? That's a wrong question. Earthquake should never be never designed for a certain magnitude of earthquake. They are designed to resist a certain intensity of shaking at that site where the structure is going to be built. Of course, there are correlations between magnitude and intensity, and many of them, but one of the most famous correlation is the Gutenberg-Richter relationship, as you can see here. So coming back to the point that there can be different levels of shaking. We kind of loosely call them as minor level of shaking, moderate level of shaking, and severe level of shaking. The other aspect is that if we look at size of earthquake, let's say for just for the sake of this discussion, we still go with magnitude as a measure of the size. We see that many earthquakes occur which are small in magnitude, and very few occur, on an average, which are very large. So there is a certain distribution of these earthquakes. So we say that, and this is where the concept of return period of earthquakes come, whereby we say that these small size earthquakes or the minor events, they occur very frequently. There are, so over a certain period of time, there will be many such small earthquakes. There will be some moderate number of, medium number of these medium size earthquakes, or what we call moderate events. And there will be very few, very large, severe events. So these minor, moderate, and severe levels of earthquakes, depending on their size, will cause small amount of or low amount of displacement loading on the structure, medium level of displacement loading on the structure, or high level of displacement loading on structure. As structural engineers, therefore, we have to design our structures to resist these different levels of shaking. So we have two basic options. The first option is we design a structure whose lateral load, lateral deformation response is as shown. That means it remains elastic, not just when the small, low level of displacement is imposed by the minor level of earthquake, but also when the very big event happens. So this is one option. The other option is we design a structure whose lateral load deformation relationship looks something like this, and notice that this structure also satisfies the displacement demands imposed by different levels of earthquakes on it. Now, if I put both the options simultaneously, which option do we choose? Remember, for the first one, this is the maximum amount of force that will be induced in the structure when the severe level of earthquake comes. Whereas for the second case, it is only this much force that will be induced. Now, we all know as designers, when we have to design for larger force, our member sizes have to be larger. We have to put a lot more reinforcement or stiffness in steel structures and so on. Whereas if the design force, if the maximum force is lesser, we can come up with more economical design. So which option do we choose? As structural designers, as earthquake engineers, we consciously choose the second option. We consciously choose the second option because now we have to provide the structure with lesser lateral force capacity. Very good. We get more economical design compared to, let's say, this one. But at what cost? Remember, whenever the lateral load deformation response bends like this point signifies damage. That means our structure will get damaged. And thus, we accept damage as a philosophical thing in earthquake resistant design. So therefore, we say that as designers, we'll design structures so that the minor frequent earthquakes will be resisted by the structure without any structural or non-structural damage. Every time there is a small earthquake, nothing should happen to my building. Nothing should, be no cracking, no spalling of concrete, no disturbance. I should be able to continue my work in my office or in my house. But when the moderate earthquake comes, there can be some damage in the structure, but that should be minor, little bit, and it should be repairable ideally. But when that very large earthquake comes, once in a lifetime kind of a situation with very large return period, then the only criterion I'm putting is that my structure should not collapse. It can get damaged. It is supposed to get damaged because as a designer, I have designed it to get damaged. But the only condition is it must not collapse. So this is where earthquake resistant design becomes so very different, so very special. But we have seen these photographs for many years now. People consolidated on this philosophy, but we fail to execute it properly, and that is why we see buildings collapsing. If it was reinforced concrete, here is a steel building. If that building did not collapse, here you have a building which 21-story steel building, which you are seeing, which collapsed during the 1985 Mexico City earthquake. If that was building, here we have bridges. If it is steel bridges, the whole thing got washed away or got crushed. Is this a problem with steel bridges? Answer is no. Concrete bridges also got equally affected. And as you can see, an entire stretch of such things can fall down. And remember this picture, I want everybody to remember, because today we are constructing something very similar to this in almost every city. So what went wrong? The only thing that went wrong is that we designed the structures, but we did not ensure, we did not guarantee that displacement capacity that is required to resist the big events. Strength is not the issue. We were supposed to provide the displacement capacity and the ductility capacity. That was where we missed the bus. So, quickly to summarize, we deliberately design structures for a much lower level of force so that we don't have to design for such a high force. So anybody who says, oh, seismic design is going to make my structure costly, actually it's wrong. The seismic design is, built in a way to bring in economy in design. Otherwise, if we want a structure which should not get damaged, that structure would have costed much more. But then we also realize that there is another issue of overstrength, because the way we design our structures, our design methods, we use partial safety factors and so on and so forth, all that gives some overstrength. So there are two issues. One is ductility and the second is the overstrength. And that is where we combine these two along with redundancy, we'll see, to reduce the force for which we actually have to design. We actually design our structures, and that we do by use of response reduction factor. Very popular item for earthquake designers. We want to use as high a response reduction factor as possible. So we first calculate the elastic force that would have been induced in the structure if it were to remain elastic, but then we don't design for that high force. We reduce it by use of response reduction. And this is where the key is. How much should the response reduction factor be? Can I reduce the force capacity to this level, this level, this level? How much? So let us understand that. If the structure were to remain elastic, that would have been the amount of force which would be induced in the structure. But we don't want that. We say, oh, that will be too costly, too costly. Design it for little lesser, give me little more economy. Fine. As a designer, you can give this as an option. You said, okay, you don't have to design for that. Your structure doesn't have to have that high capacity. It is okay to have this much strength capacity. But then that structure will now be getting damaged at that level of displacement. And therefore, there is a certain ductility requirement that comes along with the reduction in the capacity. You can say, oh, this is also too costly, give me little less. Well, now that little less comes with a little more requirement of ductility, and so on and so forth. The question is, can we go on reducing the strength requirement by promising more and more ductility? Answer is no, because there is a practical limit of how much ductility that can be put in structures. And that is where we'll see design codes come in and say, look, you have to design your structure for at least a minimum lateral force, because we cannot go on reducing the design force indefinitely. So although in earthquake resistant design, reliance is placed on deformability, which is displacement capacity and ductility capacity, design codes also talk about this basic minimum design force, at least currently. So we all know that our country is divided into 4 zones and we have these zone factors, but essentially the zones are supposed to represent the likely intensity of shaking. So zone 2 is expected to, see intensity of shaking of 6 and lower, whereas zone 5 intensity of shaking of 9 and higher. But Professor Raghukant will talk more about this particular aspect of hazard, and so I'll not touch upon that. This factor 2, Professor Murthy yesterday mentioned. I will not talk much about it, except that we are just using it. But hopefully, in times, near future, we'll sort this out and come out of that. Then, of course, we have this design spectrum, which essentially to capture the possible dynamic behavior of the structures, and then the importance factor. Now, what is this importance factor? So, as we saw, provided that deformability is provided, we can actually go on designing structures for lesser and lesser strength. But every time the strength comes down, the ductility requirement increases. It also means that this structure will see so much more damage than this blue structure. So if you do not want much damage to happen in your structure, in the situation where the strong rare event occurs, as for instance we want for important buildings like hospitals, because if the hospital building is damaged, then of course it is useless. We can't treat people who are injured during earthquakes. So if you want less damage to happen, then you have to again necessarily enhance or increase the strength capacity of the structure. And that we do by use of importance factor. And then finally, the response reduction factor that we use in the denominator to come to the design force from the elastic force that would have been induced in the structure if it were to remain elastic. Now, here our design codes, for instance, if you go to table 9 of IS1893 part 1, 2016, it will give response reduction factors for different types of structural systems. But essentially, we classify our structures into two groups. One we call ordinary, which are not so ductile, and one we call special, which are supposed to be ductile. And therefore, we use a higher response reduction factor for that. So that is the whole issue. Now the question is, so with this design, having done this design and detailing, have we ensured, have we guaranteed the displacement capacity? Have we guaranteed the ductility? That can be determined only by doing analysis and not elastic analysis, not linear elastic analysis, static or dynamic, but non-linear analysis. So this is why this slide came up yesterday, that we start with material, then you come up with cross-section, then design the members, and finally, by doing simple nonlinear analysis, even static analysis, which we only call pushover analysis, we should be able to get the load deformation curve. Just to give you a very quick example, let's say we have a simple portal with this ISMB 600 beam and column, ISMB 600 column and ISMB 250 beam. So here you see the moment capacities. Obviously, these columns have higher moment capacity, beam has lower moment capacity. And if we start applying lateral load, we know that this will be the bending moment diagram. And so if damage has to happen, it will happen where bending moment is maximum, which are at the ends of the members, at the end of the beam and at the end of the columns. Now, if we focus here, since the beam has lesser capacity than the column, as this lateral load goes on increasing, if damage has to happen, obviously it will happen in the beam. So this is what we'll get. As it is being pushed, we will see two plastic hinges will be formed in the beams for this particular case. And we will see that we can compute at what level of load and what level of deformation will this happen. So that is the load deformation graph up to that point. If we continue to push further, we will see this left end, let's say for this particular example of the column, will form a plastic hinge, and it is possible to calculate what is that load and what deformation will happen. If we continue further, eventually a plastic hinge will form at the bottom of the right column also, and that will be the load deformation. Now, if you see the last one, you see that there are 4 plastic hinges, and that means it has formed a mechanism. What will happen after this? Well, if the plastic hinges, if each of these 4 plastic hinges, if they can continue without losing strength, the structure will go on like that. But that seldom happens because real structural elements made of real materials have limited deformation capacity. So at certain point of deformation, the whole structure will start losing its lateral load capacity, strength capacity, and so it will come down. The lateral load will come down like that. So this is how typically structured nonlinear analysis is done. For simple structure, it is also possible to do such analysis by doing piecewise linear analysis. So for the first part, this green part, this is the structure we can analyze. For the second part, when the plastic hinges are formed, we can still do linear elastic analysis. For a structure which is modified like this, we will get only this increment of the load and deformation, and then subsequently this we can do analyze to get this little increment. So this is how typically pushover analysis is done to ascertain whether that required deformability and ductility is provided in the structure or not. But the basic question still remains, how do we actually provide ductility? The simplest way is to prevent all brittle modes of failures. If we can prevent in a structure all possible brittle modes of failure, the structure will not have any choice but to respond in a ductile manner. So very quickly, in reinforced concrete structures, the only mode which is ductile is under reinforced flexural action. And that is why our IS456 says over reinforced sections are prohibited. You have to design necessarily under reinforced sections. Similarly, in steel, again, flexural response only in proper sections, plastic sections. Okay, slender sections, semi-compact sections are not allowed. All other modes are generally brittle in nature. So that is about what mode of damage, where typically only in desirable actions, typically in frame buildings, frame structures, it is ideal location are the beam ends, as we saw in the previous example. So the strategy is that yes, we want to design our structures for a lesser force. Therefore, we have to allow damage. The question now is of what type. We have understood that we have to allow only ductile mode of damage, and where only in favorable locations. For instance, in a moment frame, only the beam ends are the favorable locations, not the columns. Why? Because if you see the PM interaction, and if you remember the charts in SP16, they have these radial lines also. And there is a point of what we call the balance point. If the axial load level, if the compressive load is higher than that level where the balance point is, failure is going to be by crushing of concrete. Whereas if it is below that point, then it will be by yielding of tensile steel. And yielding of tensile steel essentially is an under reinforced action, which will give you ductility. Particularly if we have small size columns, the axial load ratio will be very high, and that will give brittle mode of failure. So we do not want damage to happen in columns, because often that damage will be brittle in nature. It is only at beam ends that we allow damage which can be made ductile. Why? Also, because if we allow damage in columns, it can have very few damages. Let's say all the columns in one particular story can have damage, and we can reach a collapse mechanism. So Murthy yesterday stressed upon the importance of collapse mechanism. Whereas in the second figure, what you see is that lot of hinges can be formed, and therefore, as a whole, that structure will have lot more energy dissipation capacity. This was the seventh tenet that was shown by Professor Murthy yesterday. We essentially want the structures to have large energy dissipation capacity, so that the big earthquake, which feeds in a lot of energy into the structure is able to dissipate that faster. So we need that. How do we actually ensure this happens? And that we ensure through this concept of what is called capacity design. There are two aspects in it. One is setting a hierarchy of strength, which in turn dictates the sequence in which damage happens. In that example that we saw, beams had lesser strength capacity, moment capacity. So damage first happened in the beams. The plastic hinges were formed in the beams first. And that is how the hierarchy of strength helps in sequencing the damage. Most of you would have come across this chain analogy. What is said is that the strength and ductility of a chain depends on the strength and ductility of its weakest link. So let us say we have a chain and a force or a displacement is imposed at the ends, and we have many of one type and one, let's say just we need one in this particular example of a second type of link. And what are these? One is a brittle link, one is a ductile link, and we have two options here. The first option is that we have many strong brittle links plus one weak ductile link. So you can see that there is a hierarchy of strength. The brittle links are stronger here than the ductile link. Or we have another option where we have the weak links to be weaker, having lesser strength than the ductile link. Which option is desirable? Which option will give us an overall ductile chain? Obviously, the first one. So what we learn from here is that the brittle actions must have strength larger than the ductile action. Then only damage will happen to the ductile one, and thereby we will get a ductile response. So this is the most important concept that we have to understand. How is it applied to actual structures? Let us look at a frame structure. We have beams and columns. So now let us say we are designing a reinforced concrete frame. We design the beam, we design under reinforced beams. And so this is how we get the cross section. We design the size and we design the longitudinal reinforcement. But then we should realize that the actual moment capacity of the beam is going to be more than what we calculate it to be. So for instance, if mu is the design moment capacity, the actual, the most probable moment capacity is more than that. How much more? There is going to be, when the plastic hinge forms and curvature is increased, the steel is going to go into strain hardening. There is always a strain hardening region in steel. So that strain hardening typically is considered to be about 20% of the yield strength. That much extra stress can be generated. And remember, in calculating mu, we use partial safety factor of 1.5 for concrete and 1.15 for steel. So if we remove that, we see that the maximum moment capacity will be about 40% more than the design moment capacity. And this is the overstrength. Is overstrength always good? Having more strength is good? No, not always. And this is important because now when those plastic hinges are formed for equilibrium, the corresponding flexural overstrength based shear, equilibrating shear that will get generated will be calculated as this. And in all cases, this shear will be much more than the shear force that you would have got from your basic structural analysis. So while the flexural design is done based on the structural analysis that you did based on the design force, the shear design now has to be done for this shear and not the linear elastic shear force which you got from your analysis. This is where capacity design is done so that the beam as a whole sees flexural damage and doesn't fail by shear. Same is the case with steel. We can have steel frame and we design the cross section. In this case, we will design nice plastic cross sections as beams. But then again, the actual moment capacity can be higher, which can be this again if we consider 20% strain hardening, and if we remove the partial safety factor gamma m naught, if you remember in IS800, then we are talking about something like 30% more. But if we denote it in terms of the plastic moment capacity, not the design moment capacity, then it is about 20% more. Now, again, for equilibrium, this will be the associated shear force. But typically hot roll sections are proportioned so that they are able to resist that shear. But the point in steel is that you have also the connection to design. And thus, the connection design force now comes through the actual capacity of the ductile element, which is the beam. And now the connections have to be designed. If we don't design the connections, this, let's say the CJP welds, as was done earlier, for these enhanced forces, based on the capacity design principle, based on the capacity of the beam, then we will see failures like this, which was seen all along earlier. Not, in Japan, in US, in many countries. So capacity design becomes an integral, part of design, the rationale behind many design goals. Let us continue to focus on this beam. So now we have these plastic hinges formed, the maximum probable moment that is generated, and the equilibrating shear. But that also means that now the columns are also subjected to these forces, assuming that the point of counterflexure are at mid height. So now this is the shear force that is acting on the columns. And if we do not want our columns to fail in shear, we have to now design our columns for shear. Is this supposed to be done for reinforced concrete buildings or steel buildings? Both. It doesn't matter whether it's concrete or steel. Force action is force action. So columns have to be designed for shear, and this is important because our codes, when we design columns, unfortunately, if you ask what is a column, most people will answer it is a compression member. But no, it is not only a compression member. Columns are also subjected to bending moment and shear force, and shear being a brittle action. If we don't design our columns for shear, our columns are going to fail in a very, very brittle manner. And that is where our structures are going to be brittle. Not good. Taking it further, now if we zoom in and look at the beam column joint, then we see that for these moments that are generated in the beam, for the joint to be in equilibrium, the columns will also have these end moments. And that is how we say that now the columns have to have a capacity together to resist the maximum probable moment, not the moment that we got from our linear elastic analysis that we did for the design force, but this is the actual force which can be generated. And that is how we come up with the requirement of strong column weak beam strength ratio. So you can see both IS13920 and IS800 gives a requirement by how much column should be stronger than the beams, because this is the only way we can ensure that those nice ductile plastic hinges are formed only in the beams, columns are not damaged, and therefore the structure as a whole has higher ductility capacity and deformability. I'm sure Professor Jaya and Professor Satish Kumar will offer much more on each of these items when they speak. But I want you to focus on this two numbers and think about why are they slightly different, they're looking different. And the second question, of course, is, are they enough? Also, when we draw the bending moment diagram, we forget the size of the joint. But essentially, the bending moment diagram in the column goes through a high gradient here. And the gradient of bending moment is nothing but shear force. And this is the shear that the joints are subjected to. So in reinforced concrete, we have this beam column joint. And in steel moment frames, we have this joint panel zone, which is subjected to this very high level of shear force. And they have to be designed appropriately. If we don't design the joint panel zone and the beam column joint for this shear, then we will see that these joints can fail, and those are brittle modes of failures again, and we do not want them. So design of beam column joint and panel zone are important design issues that a designer must take care of. So essentially what I want to say is that this concept of capacity design is actually the rationale, the basic behind most design provisions in seismic design codes, not just in India, across the world. And for us, we have IS13920 for reinforced concrete structures and IS800 section 12, particularly for steel structures. But essentially, these extra provisions are required for what is called lateral load resisting systems. And there was, I believe, a question about that. What is this lateral load resisting system all about? So if I show a plan, let us say that what we are seeing right now on the screen is the typical plan of a nice rectangular building. And those are the grid marks, the beam center lines, and those are the location of columns. Which are these beams and columns that we need to design to resist earthquake? We need not design everything to design earthquake. For instance, I can choose only these 4 frames to resist earthquake in the Y direction, and only these 2 frames in the X direction to resist seismic force in the X direction. And this is what even IS13920, for instance, says. Now, the question is, how do we decide on this? Typically, what I find is that design engineers say that in some commercial softwares, we will release the end moments of the members, particularly beams. That is not the way to do it. The idea is that the identified lateral frames must draw the force onto themselves. So for instance, if we provide same size of beams and columns in all these 5 frames, each one of them will take 20% of the lateral load, total lateral load acting in this direction, the Y direction. Because with a rigid diaphragm, the distribution of load will be proportional to the stiffness of the. So we'll see that everybody, these 2 lateral frames will take only 40%, 20 plus 20, and the remaining 60% will go into this. This is not where we are seeing that these 2 are the lateral load resisting system. So what do we have to do? We have to make them stiffer. How do we make them stiffer? By increasing member sizes. Of which members? Beams and columns. But effectively, if we increase size of beams, it will not be so practical. So increasing size of columns is the way. So what you see here is that as the columns are made stiffer, now these 2 frames start drawing more and more percentage of force. And of course, we'll never reach 100%. We'll stop at some value. We can say 90%, 95%. And that is how we make a chosen frame to be the lateral load resisting system, not by releasing end moments in commercial softwares. In steel, we have to do a similar thing, but we also have a simpler choice by designing pin connections between beams and columns and not moment connections. That will help us a little bit more. So there is an importance to distinguish lateral load resisting system from the gravity load resisting systems. What is that? Essentially all the other beams and columns. They need not follow all the provisions, all the seismic design provisions, except that they have to be designed for compatibility. When the entire lateral load resisting system deforms, these members will also deform and will induce additional moments. So they have to be designed for that. So with that, I'll stop on that aspect and quickly focus on multi-story buildings that we see here. This photograph can be considered to be a view of any city, any city that we are having today. And we have lot of multi-story buildings, lots and lots of them. And this craze of multi-story building has also reached hills, as you can see. But one very key aspect in all these buildings is what you see at the bottom. And what is it that we find at the bottom? We all know the story of Kalidasa, who sat on a branch and chopped off the support. The lesson from this is that you are not supposed to weaken the support. If you do, you are going to fall. You are going to fall down. The system is going to break. And that is exactly what we are doing to our structures. It all looks nice until you focus and suddenly you see that, oh, the support has been chopped off. The whole entire sturdy building is as if being supported on these nice, flimsy, toothpick-like columns. That's the weak link. So we have the base of a building is the support, and that is looking bad, as if it has been cut off. Why do we do this? because we want parking space. Very good. We want our cars to be parked. They are very valuable position. So we have to have the ground story completely open. What has that led to? That has led to collapse. This is not a 1, 2, 3, 4-story building. This was a 5-story building, so called. There was a ground story which is no more. And same is the case. And we have seen hundreds of these buildings, collapsing during past earthquakes, even in India. These are all from the Bhuj earthquake, of course. If buildings don't collapse all the way for some reason, then we will definitely have damages which are non-repairable. You can see the damage at the base of the columns. This is not repairable by any stretch of imagination. So although the building has not collapsed, this building is now useless. It has to be brought down. Why did we see such things? We all know as lateral loads gets accumulated, the demand increases as we come down. And that is why the desired capacity should be like this. As we come down towards the base, that has higher demand, and that therefore logically thinking, the base should have higher capacity. But no, we don't provide that. What we provide is this. Stiffness is, in terms of stiffness, we provide 1/10, possibly even, worse than that. In terms of strength, we provide half, 1/3 the strength at the lower story. Why is that? Because in the upper stories, we have these so-called infill walls filled in the moment frame. But in the ground story, because we want parking, we have removed the infill frames. Now, infill frames, we kind of treat them as so-called non-structural elements. They are not. For earthquake resistance, infill frames are structural elements. They are not non-structural elements. Why? Because when the moment frame tries to swing back and forth during earthquakes, these infill frames come in their way and they say, no, you can't move, I'm here. And that is where they resist that movement. They offer stiffness, they offer strength. And that is why these infill frames are not non-structural elements. I'm repeating so many times. So what it does is essentially changes the entire load transfer mechanism. And so suddenly this open story here sees tremendous amount of moment and axial action in the columns. And that is where the columns get damaged, they fail, and the entire building comes down. So IS1893 part 1, for instance, has a separate section on buildings, and in that they talk about irregularities. And it says all efforts shall be made to eliminate irregularities by modifying architectural, planning, and structural configurations. So both architects and engineers have a responsibility here to ensure that we do not construct buildings which have these irregularities, or in other words, deficiencies, which can affect their seismic performance. I will not go into the details of it because we don't have much time, but essentially to summarize, there are two basic types of irregularities that are talked about in IS 1893 part 1. They are plan irregularities and vertical irregularities. There are 5 plan irregularities and there are 7 vertical irregularities as given in tables 5 and 6. Some of these irregularities are bad, but not so bad. You can negotiate, you can live with them, you can say, okay, fine, we will do something. But there are some which are absolutely non-negotiable, right? It's like good habits versus bad habits. You can, of course, everybody has some bad habit, but you don't go and kill people. That's not a bad habit, that's unpardonable, right? So code also distinguishes them into kind of tries to classify them and gives clear instructions as to what is to be done when you have these 12 irregularities. It gives clear strategy of how to handle them. Here I will focus only on three of them. Not that these are the most important, others are not, but for want of time, I'll just focus on three of them. In plan irregularities, one important concept is this out of plane offset in vertical elements. The figure that you are seeing on the left is the figure from the previous version of the code. It said that this is bad. And of course, this figure also was there. So what is bad here? We saw a photograph earlier where we had a wall and then the columns and the column bases got crushed. So here is the situation that there was a shear wall, RC wall, and then suddenly in the ground story, because we want this opening, we shifted this out of plane and moved it one way back. So this is what we see. The wall was coming nicely, but suddenly we want opening here. So we moved this wall here. What it does is it creates a discontinuity in load path. All the load which was coming here suddenly doesn't find the continuity of load path. The load has to turn here, go back here, and come down. And any this is like a reentrant corner. Any 90-degree bend of load path is not good. We all know from our basic mechanics class. Now, many people feel that that's okay, provided we provide this special stirrups and confining reinforcement in the columns. This is not acceptable, and that is why we need to ensure that these walls are not discontinued anymore like this, but taken all the way down. Why is, if you ask, it is simply because these columns are not good enough. We have these 9-inch columns, and these columns cannot take the load and support the weight of thick structural walls sitting on top of them, even if we provide all the confining reinforcement we want to provide. So this is not acceptable, and that is why you will see that the current revision of the code says that these structural walls will have to be necessarily taken all the way to their foundations and not be discontinued like this. Now, coming to the vertical irregularities, these are the two very critical irregularities, stiffness and strength. And this is where you talk about soft story and weak story. Softness is about flexibility, so it's related to stiffness. And weakness is related to strength. Damage is related to strength, and so weakness is also important. Which is more important? Both are important. There's nothing to choose between stiffness irregularity or strength irregularity. So what is a soft story? A soft story is one whose stiffness is less than that of the story above. We saw that demand increases as we come down. So particularly the lower story cannot have less stiffness, less stiffness capacity than the story above. So how do we capture this? Now the new revision says that you have to consider the effect of the infill wall also. And the code gives ways of how to model that. And so essentially today designer will have to create two models. One, a stiff model where the infill walls are modeled to capture stiffness irregularity, and another, the bare frame model, which we have been using traditionally to capture the moment and the bending moment and the shear force, essentially the forces, and design using both of them. Talking of strength irregularities, similarly, we saw that demand increases as we come down. So therefore, a lower story cannot have less strength capacity compared to the story above. And so today we talk about RC buildings which should not have soft story and weak story. But we need parking, don't we? So we need a story to be open. And this is where the important distinction that has to be made by engineers, which is open story is not necessarily a soft story or a weak story. So the code says these kind of buildings must mandatorily have RC walls in them, built in them. So gone are the days where we used to analyze a moment frame and construct a moment frame and then put infill walls. A designer will have to necessarily design a building with RC wall right from the beginning. How does it help? We saw that already these buildings would have these irregularities. Now, how do we eliminate this irregularity? It is already existing, 1:10, 1:2. If only we can add something that brings in lot more stiffness, let's say a wall brings in 100 times stiffness. Now the ratio 101 versus 110 is not so bad. It's not so bad as 1:10, right? This is 90% only. And similarly, in terms of strength also, we will be able to manage. And so it is important that structural walls are provided. But what happens to the parking? Well, we need structural walls not on all bays. Only in select bays we need to provide these walls, and we can still have parking, you know, in our buildings. So it is the responsibility of today of the architects and engineers to plan accordingly and design the structure properly. Of course, as a temporary measure, you can see people did infill open ground stories and they continue to use that space for parking. So Clause 710.1 of IS13920 now has, or of 1893 now has clear guidelines that open ground story buildings must be provided with RC walls in select bays, and they must be founded on properly designed foundations and not, truncated to be resting on beams and so on and so forth. And they have to be adequately connected to the moment frame. With all these, code actually is not so stringent. It gives a relaxation of about 10 to 20% in terms of stiffness and strength. But the important thing is now all buildings must have at least 2% of RC walls or walls in each planned direction. What we do in steel buildings, we should provide bracings, proper bracings, if not steel plate shear walls. But for RC walls, they have to be designed for using requirements of IS13920. Now you must have noticed that I have held on to using the word shear wall because walls behave, it depends on their behavior. If you have squat walls, shear will be the predominant action. If they are slender walls, flexural action will be the predominant action. So therefore the RC structural use of the word structural wall is more appropriate than reclassifying a wall to be either shear or flexural. It doesn't matter. All these, provisions are essentially to ensure that we have ductile action in our buildings. Our buildings are ductile. They possess that deformability, that deformation capacity to resist, to satisfy the displacement loading that will be imposed on them during that rare, infrequent, strong earthquake shaking. That is the primary objective of design codes, to prevent brittle failures. So in closing, I want all of you to take a moment to read this. Earthquake effects on structures systematically bring out the mistakes made in design and construction, even the minutest mistakes. It's a serious job. It's a very serious profession. You cannot afford. We can get away doing, a lousy job until the earthquake occurs. Therefore, my request is that while focusing on the design provisions and analysis methods are important, they are only tools. Our focus should be on understanding structural behavior. If we keep behavior in the focus, then we will be able to do justice to this field of earthquake engineering, earthquake resistant design. We need to see the big picture and not get lost in the details of these design and analysis. We need to make a beginning, particularly my appeal to the younger colleagues, students. First, try to understand the intent of the code. Learn the details associated with each clause and develop strategies on how you're going to implement them in your practice. Knowing only the clauses is not going to help. You're not going to see the big picture. We need to do this. Each one of us have to do this only to ensure that our country has a better and safer built environment. Earthquake safety in the country has to become an action by the people for the people. Today, unfortunately, when we buy any other item, we don't mind buying, spending extra. We want that big lakhs of rupees worth of LCD TV, but when it comes to buying houses, we want a cheaper house. And cheaper houses will not necessarily be an earthquake resistant house. We are putting not only ourselves, our near and dear ones, also their lives at stake. This is where academia, industry, everybody, students, teachers, engineers, we have to take this seriously enough. We have to all pitch in and participate together. In this, I'll close with this, and I'll thank, first of all, Professor Binu Sukumar and all her colleagues who had made this available, made this opportunity for all of us to come together to discuss this subject. But more importantly, I am grateful to BIS for giving an opportunity to be part of the process of writing some of these codes and get a better insight onto it. Of course, no individual is successful without help and support of many people. So teachers, colleagues, students for photographs, of course, we teachers present a lot of things which are prepared by our students, so we have to acknowledge them as well. And internet, for instance, for some of the photographs and images. In the end, I want to highlight, not that you don't know, but just to re-emphasize this particular issue, that what is the essence of education? It is not collection of facts, but rather concentration of mind. And I saw yesterday, and not just yesterday, but every time there is a seminar, there's a lot of request for PPT slides and so on and so forth. That's not going to help you. Having a PPT slide, and saving it in a folder is not going to help anyone. Don't ask for that. Ask for knowledge, ask for concepts, and that will only help you grow. So my appeal is, ask for bigger things. Don't ask for the trivials. With that, only we will be able to grow together and be, useful to our country. I'll conclude here. Thank you all for being with me today. We'll take up your questions. Jai Hind.
Thank you so much, Professor Ruben Goswami, sir. It was a wonderful session. And you correctly said that you have to take away the knowledge, whatever been shared in the session. It's not only the slides, even I have received so many requests for sharing the slides. So please, you can share your questions, you can post your questions on the question answer session, and the participant, those who are watching through YouTube, your question also will be posted here.
Sure.
Yeah.
So I can see 3 questions. I have 2 questions. Please post your questions here, okay? Difference between ductile detailing and seismic isolation, which is better? One is to dissipate that energy through ductile action. That means your structure is going to get damaged. If you can afford that as a philosophy, which we obviously use for normal structure, we don't mind that structure to get damaged. Only condition is that it must not collapse, killing people. Then doing seismic design and detailing is perfectly fine. And by the way, I want to emphasize one thing. You cannot make a structure earthquake resistant only by doing detailing. You have to do design. And that is the whole essence of capacity design. Without doing that, that is the first part. Capacity design is the first part. Without doing that, just by putting some special confining reinforcement, for instance, in reinforced concrete, is not going to make your structure earthquake resistant. So please keep this in mind. Now, in case of very important structures, let's say hospital buildings, for instance, we cannot afford to allow damage. That is where we try to reduce the effect of the earthquake on the structure so that the structure doesn't get damaged. And that is where using systems like base isolation can be effective. So you have to choose. It's not that one medicine will solve all problems. You have to do the diagnosis and then give appropriate medicine. Just like our medical professionals do, we also as earthquake, engineers and structural engineers, we also have to do that. We will not recommend the same medicine for every situation. Okay. I'll skip the part of the the cost. Cost is not something that we can discuss so easily in such a short time. Is it advisable to release moments in beams in weaker axis direction of 9-inch columns, or is it better? Is there a detailing which will ensure that that particular behavior will happen? If no, we should not. We should create, that is the whole intent. The purpose of analysis is to reflect structural behavior. If we know that the structural behavior is going to be something different, we should not try to simulate wrong behavior through our analysis. That's the golden rule, right? And the intent of design is to control behavior. Through design, we want to control behavior. We want the structure to behave the way we want. And the purpose of doing analysis is to reflect the actual behavior that the structure would demonstrate. It is not to simulate something irrational. So we will not do that. The connection mechanism between ductile columns and gravity columns by way of beams, it is difficult to express. Maybe on another occasion we'll do, but basically, if it is a reinforced concrete, the compatibility is the important issue here. So when the ductile columns, the lateral load resisting frame deforms, we have to, if it is a reinforced concrete, reinforcements will be taken into. Continuity of reinforcement have to be provided, anchorage has to be provided, otherwise there will be slippage, and that's a brittle mode of action we saw. We cannot afford to have slippage of reinforcing bars by not providing adequate anchorage. So obviously now the only issue that is left is to ensure that compatibility of deformation is honored and appropriately designed. When will Indian standard provide standards with details like ATC 40 and FEMA 360 over pushover analysis? Today, if I may be wrong in my estimate, but not more than about 7 to 8 engineering colleges across India, and this is including probably in IITs, who teach nonlinear analysis as part of mandatory curriculum of MTech engineering, MTech structural engineering. So unless we as a country do that, how can design codes mandatorily ask pushover analysis to be done for every design? We are not trained yet. We have to enhance our education level. We have to have even earthquake engineering as part of mandatory curriculum of MTech, ME programs. Then only we can think of doing all that. Until such time, that is why Professor Murthy yesterday showed the entire spectrum of seismic design codes. We are still at the strength level with capacity design as a stopgap arrangement only. And we'll continue to do that until we improve ourselves in terms of having better education on these aspects. For reinforced concrete members, what is the range specified in the code for low ductility, medium ductility, strong ductility? As of now, we are supposed to follow the seismic design provisions of IS13920 and section 12. And these ranges, we don't do medium and strong. We classify our structures only in two broad categories, which are ordinary and special. We are not able to do fine tuning as some of the other international codes are doing in having three categories: ordinary, intermediate, and special. We will continue for some time with only two broad categories. And so that we will assume that it is satisfied if we follow all the capacity design provisions and do all the proper ductile detailing, follow the detailing requirements. In beam column joint, which one will be the critical interior or exterior? Obviously, interior ones are more critical because you have two beams from two sides, imposing this this moment in opposite directions. So, typically, interior joints, beam column joints are more critical in design. But of course, it depends on the size of the members and the actual design and so on and so forth. But yes, but typically it is the interior ones which are more critical. As per functional requirements in some structures, like five-star hotels, transfer girders are required at some levels. Can we accommodate this? Again, the question is, what is the minimum average of all of us? And when I say all of us, not just who have logged in today, but all the engineers in the country. We have a large amount of just graduated engineers in the country who are designing structures and who are signing structures. So for them, it would be a difficult task to appropriately design a transfer girder and so on. So that is why we need experienced engineers. And if you are an experienced engineer, yes, theoretically speaking, any structure can be designed. But the codes are there to ensure that those who are not experienced, those who are not so capable, they do not make bad mistakes. And that is why design codes are. So design codes are not recommendations aimed at the topmost engineers in the country. Rather, they are to protect the not so capable, inexperienced young engineers. And that is why, yes, as a theoretical answer, yes, it is possible to design transfer girders, but it is not openly recommended. Because then anybody and everybody will start doing that and they will make mistakes and structures and buildings will start collapsing. Not good thing. Why is IS1893 2015 part 4 scale factor is ignored? Well, part 4 is for industrial things. Let us not go into that right now. Let us focus on what we have discussed through this presentation. There may be another occasion to discuss industrial structures and those issues. Why is pin joint considered for steel frames and a rigid joint for RC frames? Because in steel frames, we know how to design a pin connection, but in reinforced concrete, we are not very sure how to do that. That's the simple reason. Why live loads are considered 25% or 50% while calculating seismic load? It's an issue of probability. The live loads which are there, of course, are supposed to be the characteristic loads. That means they are 5 percentile loads. That is, in 95% of the cases, actual loads should not be, not more than 5% cases, the actual load should be more. So they are 95 percentile cases, which is very high. The average load will obviously be lesser, and it is very unlikely that exactly at the moment the earthquake is happening, the live load will be to its full maximum. So considering this fact that just like yesterday we are discussing why we don't consider maximum wind and maximum earthquake to be occurring simultaneously. Similar is the case that it is very unlikely that the building will be seeing the maximum live load and exactly at the same time the earthquake will come, which by the way will have a very large return period. And you will learn more about return periods from Professor Daukan. So that is why we don't consider. That is why you say we can consider some reduction for the purpose of design. Not that in actual case it cannot happen, but for the purpose of structural design, we take a call here. Okay. In many cases, bringing second mode to non-torsional mode becomes difficult, but first and third modes are not torsional modes. Is it fine? There is no clear yes or no answer for some of these things. When you say torsional mode, what is torsional mode? How do you define that torsional mode is important? What are the mass participation factors? It is important. So without looking at, it's like you have to read this ECG, the whole ECG of a patient to make any comment. You just can't say, I have done an ECG, is the patient fine or not? That can't be answered like that. in many cases bringing, okay, what is the difference between P delta and pushover analysis? P delta analysis can still be done. A pushover analysis, I'll first talk, is essentially done to understand post yield inelastic response. Within that, when deformation is increasing in the inelastic condition, can P delta happen? P delta effect happen? Yes, of course it is happening. So pushover analysis should also include P delta analysis within itself. But even if it is a slender elastic structure, under elastic deformation also, P small delta and P capital delta can happen. So that is the fundamental difference. Pushover analysis is generally done for inelastic systems, whereas P delta are for both elastic as well as inelastic systems. Is floating column allowed as per IS1893? Answer is no. If you are thinking of providing a floating column, which is part of the lateral load resisting system. If it is not part of lateral load resisting system, it's your decision as a designer what to do. Floating column system to be strictly should not be allowed, and it made mandatory in code as it will create soft storing structure. No, it is not mandatory. It is not allowed. So it is very clear that floating column it should not be part of lateral load resisting system. That is the whole point. Acceptance of flat slab and PT slabs in seismic conditions. What is the question? Is it acceptable? Is it not acceptable? See, you have to start from the beginning. When you say seismic conditions, we saw that, and you will see again that there are different parts of the country and different parts of the world which have different levels of seismicity. So, something that is applicable, for instance, in a low seismic region, obviously is not applicable for a region which is highly active, seismically active. So all are seismic design. Some are low seismic regions of low seismicity, some are regions of high seismicity. In regions of high seismicity, past experience has shown that both flat slab systems and PT slab systems have failed miserably. This is past experience. This is not anybody's opinion, but past experience. So obviously, when we have a bad experience, we should be more careful in using those systems, particularly in regions of high seismicity. In low seismicity, possibly it can be allowed, but with some restrictions, with some additional precautions taken, and that is what IS1893 is trying to bring in through by restricting, for example, drift limits, by putting additional requirements of having a dual system, and so on and so forth. For long span beam with column in roof, it's difficult to attain 1.4 moment capacity of column. Then beam leads to, okay. Yesterday, Professor Murthy showed a pushover curve of a multi-story building and showed that the top portion, in the top portion, plastic hinges were not forming. Typically, the design that we do, and when I say we, it's not just we Indians, but mostly across the world, the design that is done will not push a plastic hinge to the roof level. This is general comment. Of course, design can be done to have a different behavior, but mostly this is how it is going to happen. So therefore, mostly you will see design codes will say that the column to beam strength requirement is not applicable at the roof level. That is the basis of it. Okay. Can somebody just, okay. Which do you prefer to resist seismic strength, the reinforcement or going to allow plastic hinge in some members in buildings? The structural system to resist prefer and why value are it depends on the requirements, but essentially what today we find is, and there are other countries who have shown precedents that typically when structural walls are provided in buildings, those buildings generally do not collapse. So that experience we can borrow from others and say that yes, we need that. Base isolation increases time period, but increasing time period sometimes will not have buildings will not say buildings. How can we use base isolation effectively? Well, as Professor Murthy mentioned yesterday, we are going to have a Indian standard on base isolation. Let us wait for that to come out. It will be soon put up for public comment, and then we can have a discussion on that. Pre-stress members or general member, which member is best for earthquake resistance? One thing we have to understand that this earthquake shaking can come from any direction, and essentially, therefore, it leads to reversal of stresses. Generally, when we design pre-stress, we assume a tension side, we assume a compression side, and the pre-stressing cable is provided so that we minimize tensile stresses. Now, imagine during earthquakes, if the whole beam goes in the reverse direction and stress reversal has to happen, obviously your pre-stressing will not work. So therefore, as a general statement, reinforced concrete members with the ideal is equal reinforcement on both faces is the ideal candidate to resist earthquake to resist strong earthquakes. How to make floating as non-LLS, LFRS in actual building? Well, there are many ways. You have to start by looking at the plan of the building and identify your lateral load resisting system, provide stiffness to lateral load resisting system. So there is a whole lot of process that you have to do to finally achieve that. Obviously, I'm not in a position to explain it orally without anything. It's a case-specific situation and which has to be handled. Which point or new clause will add in code for better improvement? Well, sky is the limit. We can do what is possible, and every revision of the code will try to raise the bar by a little amount, not by a large amount. So we will see how far we go. But the practice, it's not just improving a code which is going to solve the problem that we have in our country. It is the practice, the education, which also has to rise to the occasion. And all three has to do, then only will succeed collectively. For open ground story building, instead of RCC wall, shall we increase column size, stiffness of the building? You can, but there is a limit. You can't go on increasing column sizes. Then you will reach a point where columns from two sides of the bay will come and hit each other. That becomes a wall. So walls are much more effective than even larger size columns. There is a question. If the application of temperature in the column, which will be the critical joint interior? Well, that analysis has to be done, and once you do the analysis, you will see which is the critical one. It depends on the plan. It's a general statement cannot be made on some of these items. You have to. It's a structure specific. You can have a very different configuration of the layout of the structure, and that will lead to different situations. So you have to do analysis to reflect the actual behavior and then design appropriately. What is the difference between force-based design and strength-based design? Well, if I'm reading what you have written, force and strength, ideally, I thought both are same. But if you wanted to write displacement-based design, that of course is where we focus on the displacement capacity and then ensure that the displacement capacity is adequate to satisfy the displacement demand imposed by the earthquake. But in force-based design, what we essentially do is we don't go to the end of the loop, but rather we do capacity design and we do ductile detailing, and then we believe that by doing all this, we will satisfy the displacement. That's the difference. Please discuss team damper, which is best? Let us not, my request is, let us not discuss damper, because it's, as I said, it's a different concept where we do not want damage in the structure, and therefore we are trying to handle or take care of the earthquake through different means. That is not what we discussed today in this particular seminar, nor what you are going to hear in the coming lectures on steel buildings and concrete buildings, because the IS codes are still on the concept that the structure will get damaged, and therefore only through ductile action we will be resisting the earthquake. A new Indian standard on base isolation and all these things are going to come in the future, and then we'll discuss all that. Can we trust the design and analysis data of structure using commercial software? Well, commercial software, see, they are also in the business. So it is unlikely they will knowingly give a software which will give wrong results. They don't want that to happen to their customers. So they are working very hard to give you a commercial software which will give the best possible correct analysis. But of course, it is the responsibility eventually of you as an end user to kind of satisfy yourself that yes, whatever software you are purchasing or using is good enough for your purpose. So that's your responsibility. What is the difference between normal shear wall and coupled shear wall? Oh, normal shear, you can have one wall or you can have two walls which are interconnected by, what is called coupling beams. So then both of them start acting together. So that is what coupling shear wall is, and IS13920 has provisions on that, and I'm sure you will come across those in coming lectures. What is the spacing between shear walls to make it uncoupled? It's the flexibility of the coupling beam which determines whether both these walls will act together or not. So that is the whole thing. You have to do analysis to understand how the frame, how the walls are interacting with each other, and how the wall is interacting with the moment frame, to which it is connected. So that interaction has to be understood, and you can try to understand that by doing structural analysis. Any clause is there for roof 1.4 beam column joint is not applicable. It is there in the code itself. Please read. It's there already in the code. Yeah. So any more questions?
So I think you have answered all the questions which has been posted here.
Great.
So yeah, thank you so much, Professor, for the kind acceptance, and I think they are posting few more questions.
Thank you. Thank you, everyone. Have a great day. Namaskar.
Okay, so thank you so much, and thank you all the participants, those who are viewing from YouTube as well as through Zoom, and the professors, Professor C.V.M. Murthy sir, and Jaya ma'am, Satish Kumar sir, and Rikukant sir, and for your kind presence over here. And we will be eagerly waiting for the other three esteemed professors, waiting for the further 3 more sessions. And thank you so much, Ruben Goswami sir, and the assessment questions and the feedback questions are posted in the link, and it will be sent to your mail, and before at 2 p.m. every day after the end of the session. And please answer to those questions for the assessment, and do watch all the 5 sessions. Thank you so much. Thank you so much for your patient listening. Thank you, sir.
Thank you.
Thank you, sir.